hard to believe, really, that just 3 years ago, a handful of us moved from a tiny, cramped office full of computers just up the road into a completely empty industrial unit that would become DC1. In here, in just a matter of months, we built our entire facility, we built our team, we built our precision temperature-controlled machine shop, our avionics development center, our metrology lab, our power electronics lab, our design suite, our development suite, and all of the other facilities that we've needed to develop HX50 and GT50. With those facilities, we developed the capability to make aerospace quality gears, aerospace quality bearings, all of the components necessary for GT50 and all of the power electronics and software capabilities. But very quickly, we ran out of space again. Within just a year, we'd opened DC2 and DC3 that enabled us to make composite molds, composite patterns, infuse full airframes, all of our laminating capabilities, and eventually produced 2 HX50 airframes, fully fitted and ready for public display. But again, we're now running out of space. The team's growing, the facilities are growing, and it's time to step it up again. Welcome to PC1, our brand new 76,000 square foot production facility right here in the heart of Stafford. We now have the entire Hill team based here under one roof, all of our design staff, our development staff, our production staff, and our admin support staff as well, all here working under one culture with one key goal of getting the development finished and the aircraft into production. Within this facility, we will complete all of the development, all of the approvals, and then commence early series production of HX50. And beyond that, the facility will become one of the elements of our modular approach to production. These facilities don't build themselves. We've started again here with an empty box, albeit a bigger box, but we've now got to go ahead and build yet another helicopter factory. So over the course of the last few months, we've been essentially completing the design and development of our production facility for the early prototype aircraft and then the early series production aircraft, laying out the factory floor, laying out all of the other facilities that we need in here for design, development, approvals, all of the business administrative functions, customer care and support. All of that has now been designed and we're in the process now of implementing it. So if we take a look at the shop floor first, then from an empty box, we've had to add all of the electrical power infrastructure needed to locate this big, heavy-duty industrial equipment that we need. Large, heavy-duty cables running the full length of the factory, similarly with compressed air lines, with water lines, and all the other services that we need to support the wide array of manufacturing equipment that we need within the factory. In addition to that, we've had to lay down specialist foundations to support the heavy production equipment that we've installed here at PC1. The large gantry mill, this is a 15 by 15 meter machine, that has a specialist foundation and specialist ground attachments, as well as all of our precision CNC machines that you've seen before at DC1. All of those machines have had specialist foundations implemented here. We'll shortly be completing our mezzanine floor to create an environmentally enclosed chamber around them to hold those temperature controls that we've shown that we need to hit the tolerances for gears and bearings and other precision components. This is our all-new composites gantry mill. Arrived from Italy in 5 5 articulated lorry loads. It's taken a team of engineers 6 weeks to painstakingly build it. It sits on a trench that we excavated 1 metre deep to build a machine foundation strong enough and stiff enough to support the bed and the pillars to maintain the accuracy and the tolerances needed to produce accurate composites, patterns and moulds. It requires a complex web of electrical, pneumatic and control services fed to it from around the factory to control its many systems. It lives, or it creates, its own environment to contain all of the powder and dust that it makes as it manufactures high quality patterns and moulds from powder-based, polystyrene-based and model board-based materials. And then it has its own dust extraction system that palletizes that waste and keeps it all out of the factory, avoiding contaminating the clean areas of the rest of the production facility. Why would we go to such extreme lengths for a machine like this? It's quite simple. If you want to control the cost of your composite components, you have to control that process from end to end. You have to be able to make patterns, molds and parts all the way through to finished painted goods if you want to truly control the costs. And to do that, if you're going to make big composite parts, you've got to make big composite molds. If you want to make big composite molds, you're going to need to make big composite patterns. And big composite patterns require a massive gantry mill. This machine is able to produce patterns that essentially are 4 meters wide, 8 meters long, and up to 2 meters high. So anything that we could possibly dream of doing for HX50 and a good deal of our future products. Beyond that, in production, the machine is also able to keep up with over 500 machines a year in terms of the finished composite part trimming, all of the glazing trimming, and a variety of other operations to make sure that our finished composite structures are the most accurate that they can possibly be. In addition to that, this machine represents a huge step up for us in a whole host of other areas. Fundamentally, this state-of-art 5-axis machine is able to hold just 10 microns in positional accuracy over the space of about 1 meter. This means that the accuracy with which we can make our patterns and molds is far, far higher than it has ever been before. But more importantly, the quality of the flowing A surfaces that we make will be absolutely perfect, needing the absolute minimum of hand finishing to give you that silky feel to the external contours of HX50. But it's not just about the quality, it's more than that. In addition to the surface quality that this machine allows us to generate, the reliability will be second to none. So if you remember in the early stages of building the first generation of patterns and molds for HX50, our single biggest challenge was that the second-hand gantry mill that we'd bought during COVID was simply so unreliable that we had to nurse it through every manufacturing operation. All of that stops here. This is a completely self-contained, modern, reliable machine. It's capable of running 24 hours a day. As you can see, it has a modern high-speed spindle. We have remote monitoring of the machine, as well as computer controls from external stations, and we have a modern 16-tool tool changer. What that means is whereas previously we'd have had to stop programs to change tools, in this, with this machine, we can now do everything from roughing through to the sculpting of the surfaces, through to picking out intricate details and fillet radiuses, all within a single program, all within an operation, all lights out overnight. So what that means for us is both in terms of patterns and molds, we can take simple, low-cost tooling materials, such as the materials waiting to be processed over here, our conventional polyboard for the big patterns that we make, and higher grade model boards and foams, low-cost composite materials in through the front door, high quality, precision aerospace patterns and molds made in-house, right here, production ready at PC1. Let's talk about GT50, the heart of HX50. So the primary focus of the engine team at the moment is getting as much of the developed hardware onto the test bench as early as possible to validate and prove that each of the elements of the engine are working as designed and as intended. Over the course of the last few weeks, we've reported that all of the internal elements of our starter generator unit have been manufactured. All of the electrical components, the stator, the rotor, the magnetics, the coils, all of those things have been produced and are now ready to be assembled and tested. We've been producing the external casing components here in-house, and now that we've got the machine shop back online, those final components are now trickling through. So we've got the main casing, the end cap and the front cap. These in production are cast components that then have second stage machining operations on them. For the purposes of the first prototype starter generators, we've rapid prototyped as an analogy to casting and then machined those right here in the new PC1 machine shop. So the last of these components will be going through the facility over the course of the next week or two, just in time for our high-speed test bench to arrive and be commissioned just over there in the development test area. Once we've got the test bench operational, the first starter generator for GT50 can be fired up and tested throughout its entire operating range, along with the power management unit that controls and manages the starter generator and chops up and reprocesses all of that high voltage, high frequency AC electric that it generates back down into usable 28 volts DC. If we then talk about the speed reduction gearbox, the next area that we're pushing through the machine shop at the moment is the speed reduction gearbox that takes power from the power turbine at 35,000 RPM and brings that down into a more usable 5,000 or 6,000 RPM. The challenge with the gears is because at the moment we're still relying on external subcontractors for some of the plating and hardening processes. This is actually a 16-week manufacturing process to get the gears done. Over the last month or so, all of these gears have been released out into production. The blanks have been prepared and these are now busily off being copper plated ahead of coming back to us for tooth cutting and then subsequent hardening. With the gears and the casings and the shafts all released, the guys have then turned their attention to the test rig design for the drivetrain, because as soon as that gets here, this will be built up and we have to prove that that speed reduction gearbox can stand up to the duty and the performance that we need before we can run it with the whole engine as a system. So we're currently developing a system where we can wind that gearbox up and essentially run that throughout its entire operating life to validate the life of the gears, the bearings, qualify the lubrication system and validate the overall performance and strength of the system. While Craig and Rob have been focused on getting the speed reduction gearbox out of design and into production so that we can produce these components as fast as possible, the remainder of the team have been focused on the core of the turbo machinery. The compressor impeller has been ready for some time now, and we're really now just waiting for the climate controls to go back into the machine shop so we can do the finished machining operations on the turbine ready for test. The compressor disc and a lot of the core shaft components have been mature for some time, and again we're really just waiting now to get the machine shop back online to be able to produce that. One of the areas that's developed extremely rapidly over the course of the last month or so has been our in-house casting processes to produce high integrity super alloy cast turbine blades. Casting's a pretty horrible process in principle. The idea of pouring molten metal into a mold which is flowing turbulently and entraining all sorts of horrible stuff with it, controlling that is not a simple thing to do and requires a lot of careful design of the process. What we've been doing over the course of the last couple of weeks in particular is refining the filling system that allows us to very smoothly and cleanly get high quality metal out of the crucible and then down into the filling system through a series of filters, and then to gently and smoothly fill the blade cavities to create good quality defect-free turbine blades. In order to do that, we've had to do extensive design work on the filling system, the integration of our molds with the actual casting machines that we're purchasing to produce these things. We've had to develop specific high temperature seals and gaskets to be able to seal the mold cavities to the casting machine itself, and then we've been doing an extensive amount of work on optimizing the process parameters itself, including tweaking the moulding temperatures, tweaking the superheat temperatures, and controlling all of the temperatures and timescales that are necessary to control the casting process to the tightest of details. In addition to the core development of the process, we've also been equipping PC1 with all of the equipment necessary to cast turbine blades in-house. So we've now received delivery of our first casting furnace. This is a mould heating furnace, and what this allows us to do is it allows us to heat the moulds that we use to create the turbine blades to really high temperatures to ensure that the liquid metal remains liquid long enough to fully fill the casting cavities within the moulds. In order to do that, we've also created specific flasks and all of the arrangements to attach our moulds to the casting machines, preheat them in the preheating furnace, and then the apparatus to transfer them into the casting machine for pouring, filling, and cooling and solidification. Clearly this furnace isn't big enough for production. This one, once it's finished its development tasks, will become part of our quality procedures for checking various elements of the casting process. We've simultaneously ordered a much bigger unit that's capable of producing the volume of blades that we need to in early production. The reason we've bought this one now is simply because it's available today, so it allows us to complete the development of the in-house casting processes, and more importantly, go over to Germany in the course of the next couple of weeks and do the factory acceptance tests on the actual melting, pouring, casting and solidification machines that we'll be using to manufacture the Hill high pressure and low pressure turbine blades for GT50. One of the areas that's received extensive testing over the course of the last month or so has been the integration of the fuel nozzles with the swirler system that promotes a swirling turbulent flow at the back of the combustion chamber. This flow is intended to create a stable recirculating flow back here that promotes the ignition of the fire from one fuel injector to the next all the way around the annulus, and make sure that that heat remains at the back of the combustor where fresh fuel is consistently injected. That same turbulence then propagates down the combustion chamber and allows the mixing of the dilution air that comes in through the large holes in the surface of the combustor to create a nice uniform hot gas stream to feed the compressor turbine. This work has involved a combination of extensive, sophisticated simulation work and a lot of basic testing back on the bench to verify that what we see in the simulations is what we're getting in the engine. Off the back of this work now, we have a robust swirler design. We've managed to improve the flow around the combustion chamber so that we get as uniform a flow as is humanly possible within the constraints of the packaging, and we've got a nice stable flame giving good flame temperature, good metal temperature, reliable ignition and reliable stable combustion all the way through the range of operations that we're able to cover on the first rig. In addition to the optimization of the swirler arrangement, we've now also completed the development of a duplex nozzle. A duplex nozzle is a nozzle system that takes two simplex nozzles and combines them in a coannular arrangement. Now, why that's important is because in order to get effective atomization at the low fuel flow rates that you need to start the engine, you need a much smaller nozzle orifice than you do for delivering all of the fuel that you need at the high power end of the engine. Now, to make that work uniformly and smoothly across the operating range, we've combined these two things into a duplex nozzle arrangement and packaged that within the swirler that's required to create the stable combustion at the back of the combustor. Pavel's developed the geometry for that, and we're currently going through the first stages of producing the very first production grade combined duplex nozzles for the engine. These are the nozzles that will run in the second set of combustor tests and in the full gas generator tests. You've followed us producing the annular combustor over the course of several months now, and this is one of those components that it's relatively difficult to develop all of the processes that you need to create all of these rolled profiles, pressed profiles, spun profiles to the tight tolerances in the extremely tough materials that are used to survive in these extremely aggressive environments. We finally managed to finish the last of the difficult components that was proving very challenging to form, and we've now produced all of the components necessary to make a full annular combustor. So the next stage for this is to produce a set of these components, set them up in the rig that we've shown you previously, and then we can go about essentially creating all of the welds between the individual leaves to turn this into one solid annular body, ready for drilling, ready for the installation of the fuel nozzles and for testing on the rig. So, next steps for the GT50 program. With the last components for the starter generator going through the machine shop as we speak, and the test rig for the system on its way to us, ready for installation right over there in the test area here at PC1, our very next task will be to get the starter generator and its control system, the power management unit, on test and working properly. While that's going on, we'll be completing the build and then the testing of the speed reduction gearbox and the entire GT50 drivetrain, qualifying that for running both with the whole engine and then later for flight tests. While that's been going on, the team is extensively focused on getting the last few components of the combustion system working and the whole gas generator on the bench and running, generating 500 horsepower. And that will then lead kindly on to getting the whole engine working and running as a unit for the first time on the test bench.